Optimization is just using an application of absolute maximum minimum. If you recall, with absolute maximum minimum, you had to find where the derivative was equal to 0 within the domain, and then check the values of the function at endpoints. And whoever's largest wins absolute max, whoever's smallest wins absolute min. Now, I'm going to go through the problem, this first problem. And after I go through this first problem with you, I'm going to explain how little you actually need to do. But I want to express the thoroughness of the depth of what these problems are intending. So we have a farmer with 2,400 feet of fencing, and I can't get my screen to move. Why is it not listening to me? Okay, my computer's having lag time, I think. Yep. Okay, finished with your lag? Okay. Move. All right, just move how you want then. So I've got some diagrams ready. I think I see what just happened. Okay. So a farmer wants to fence off a rectangular field, but there's a river that is bordering one of those sides of the rectangle. And this farmer needs to minimize the amount of fencing used and needs, or no, sorry. I'm thinking of another problem. I need to read the problem. He needs no fence along the river. What are the dimensions of the field that has the largest area? Your first goal on these problems is, what are they asking me to optimize? Everything in my computer is lagging at this moment. All right. So what am I trying to optimize? Get a formula for what you're trying to optimize. The area of a rectangle is going to be the multiplication of its two dimensions. So I'm going to draw the three sides, understanding that, this is a rectangle with four sides, but those are the only three sides with fence. I'm going to make X be horizontal and Y be vertical just because it makes, sense. So that means area of the rectangle is X times Y. While we're in single variable calculus, you have to get an equation for what you're optimizing based on one variable, a single variable input. So there's enough information here to turn this into single variable. So you got to go back and then read everything there and put it. I can tell it's lagging right now, and it's okay. Maybe it's not. Okay. The farmer has 24 feet of fencing. If there's 24 feet of fencing, then that means that X plus 2Ys are going to add together to make 2,400. This gives a relationship between the two dimensions, but the focus of the problem is they're asking you to optimize something, and that's area. Your focus is the area formula. And you use this other formula to get this in terms of one variable. Your options are either isolate X and plug it into this X, or isolate Y and plug it into this Y. Your choice will make it either a fraction or not a fraction. So I will tell you what I prefer. I prefer the non-fractional way. The non-fractional way would be if I isolate this X, I don't have to do a division by 2. That means my area formula will then be Now I have my area formula in terms of one variable. I can take the derivative right now if I want, but I'd rather make it easier for myself and expand this. Before I go into the derivative taking, though, I have found over the years that for you guys to fully understand what you're actually doing, I need to take a moment to talk to you about what this is and how we're using absolute minimum maximum to solve the word problem. We have one input variable. That one input variable is whatever the dimension is that gets two sides. Now, that vertical length has a domain. Now, it could be 0, and then we have optimized area in the minimum sense. Is there a maximum that y can be if I have 24 feet of fencing, or 2,400 feet? Almost. Y has to show up twice. So if there are two sides that have to add together, right, you got it. So y has a closed interval domain, and a is a continuous function. So think back to when we did optimization problems, and we just had some random equation that we didn't know what it represented, and a particular closed interval to figure out where the maximum is. We needed to find the critical numbers in between the endpoints and then find the actual values of that function at critical numbers and endpoints and figure out who's largest, who's smallest. So I've got prepared a graph. And by the way, I'm going to need to make some more videos over the weekend. I didn't get to a homework video that I was going to get to yesterday, but I will try to get that uploaded over the weekend, as well as more video on this optimization. And I've got ready to go the textbook problems to show you what we are working with. And I'm changing this. Just give me a second. And then that one's going to be 1,500 and 1 million. Okay. So this is a graph of that function for area. In Desmos, I had to use X for the input variable because it just won't accept Y in that way. So you have to keep in mind that as I look at this graph, the X that I'm using here is actually the Y that I had in the other equation. The vertical Y value here is representing the area of that rectangle. Using this graph, we can actually see that we are going to get at the largest 720,000 square, I forget what dimension or what units, but square something of area that will optimize it. Thank you, feet. And I can also see that the optimization is going to happen when the input variable is 600 feet. So take a good look at this graph, but understand that when you do optimization problems, you're typically not going to have a calculator to graph for you, but you want to realize that this is what you're dealing with. You're technically dealing with the graph of a function, area in this case, with respect to an input variable, which is technically y right now, even though we see it visually as x. and that we need to find the largest value of that y value function, which is area again, not y. And so taking the derivative and setting it equal to 0 will find me this spot. Technically, I'm supposed to, for an optimization problem, also check endpoints. I've got 0 area at one endpoint and 0 area at the other. Shocking. But this is what's going on behind the scenes that you will most likely not have access to. So I'm going back to the problem. And what you're going to be expected to do is take the derivative of area with respect to y. Whatever the input variable is, you go with respect to that. And you're looking for when is that equation equal to 0, and solve. Do you see that we're getting 600 if we solve that equation? If this were a multiple choice problem, about all you would do if this was multiple choice is you would have to come up with these two equations, get it set up, take its derivative, solve for it being 0, and then figure out what was the question they asked me. Because in multiple choice, you don't have to show your work. You can do as little or as much as you want. You don't have to show that you're actually reasoning properly, which is why I do not like multiple choice.
Well, I mean, also, this problem creates like a parabola.
Yeah.
You could literally just solve for the vertex of it.
Oh, yes, absolutely. Oh,
You
yeah.
don't need to use calculus for this.
No, you don't.
Multiple choice, they don't know if you're using calculus.
Exactly. So if it's a multiple choice problem, find your shortest route through the problem and leave it alone. They typically don't give you a problem like this, though, because they know that you can solve it in an easier way. They do try to give you problems that aren't as straightforward. This is just example 1, so it's example 1's usually more simple. Let's see. So again, on multiple choice, get through it quickly but accurately, and you don't have to sit around worrying about the domain over there. It's almost feels like a waste of time. Now, if you are testing on this in a free response setting, you need to justify yourself. If it's the AP test, you really need to justify yourself. I will tell you that for me, I don't go overboard on these problems because I feel like it becomes anti-logical when it goes too far. You should be able to look at this and make enough logical sense to recognize that 600 is where it's optimizing without needing to go through an explanation of the domain possibilities of that y dimension, and then checking to see which one gives you the largest area. It should be logically obvious. So on my tests, I don't get too picky about that. But what you need to understand is if this were to show up on a free response on the AP test, they want to see your calculus. So you need to write those equations, get it all set into one equation. You've got to take the derivative, set it equal to 0, and solve. Then you have to justify. To justify, you need to know something about the domain of the input variable. Then from there, in this particular situation, it would be sufficient if you said area for y value 0, area for y value 600, and area for y value 1200. And write down the 3 areas you get. 600 was 70. Does anyone remember it off the top of their head, or do I need to go back? 70-something thousand. Thank you. So I should probably check it then. 720,000. Ooh, good memory. This would be enough justification on the AP exam for you to then say that the area optimizes when y is 600. But then you need to make sure to answer the question. The question asked, what are the dimensions of the field with that largest area? You already know the y dimension, so 600 by, and if you know what y is, what does that make x? If y is 600, y is 1200. So 600 feet by 1200 feet are the dimensions, and that answers the question. So I'm hoping you feel clear about what is expected of you with work at different levels between multiple choice, my test, and the AP test. And the figures. By figures, do you mean what's showing on the screen right now?
Like the pictures, like the 3 little boxes.
These? Oh, they're just trying to show, like, hey, if you make y too small, you won't have very much area. If you make y too big, you won't have very much area. If you go in a medium area for y, you're going to get a better, closer to optimized. They're just trying to kind of show you the idea of why you're taking the derivative and just what's going on. Okay, are we good to move to a next problem? And also, can someone warn me when we are 10 minutes before class being over, because I just cannot do Fridays and their different time frames. It messes with me too much. Okay, example 2. Whatever 10 minutes is before the time we get out. So with example 2, we want to look at what do they want us to minimize or maximize. This says find the dimensions that will minimize the cost of the metal to manufacture the can. So basically what they're describing is maybe you take some flat piece of metal and you make shapes, and then the metal folds together to make a cylindrical can. So with that in mind, minimizing the cost means minimizing the
Surface area.
Yay! Correct. So then you know your goal is to come up with an equation for surface area. Now it's a full can of oil. So we've got a top, a bottom, and then the round sides. The top and the bottom are circles. So the surface area of each of those is area of a circle, which you know to be pi r squared. There are 2 of them, so I'm multiplying by 2. And then we have the lateral surface area. But if you've ever peeled a label off a can, you know that that is actually a rectangle. The height of that cylinder is one of the dimensions of the rectangle. And can you tell me what the other dimension comes from?
Circumference of the circle.
Woo woo! Circumference. And what is the formula for circumference of a circle? Excellent. 2 pi r. Now I'm ready to add to my surface area of 2 pi r squared, 2 pi r times h, the area of that rectangle. So that's like a big step that we just finished here. We have a formula for what we are trying to minimize, but there are two variables. So I need to figure out what other information was involved in the problem that I haven't used yet that will allow me to figure out how to get rid of one of the variables. Now, the problem told you that the can needs to hold 1 liter of oil. What they failed to explain to you was that you needed to convert 1 liter into 1,000 centimeters or cubic centimeters. So I wrote that down as my little reminder so that I wouldn't forget and have to go remembering what the conversion is for liters. And my test and the AP test will never ask you to do conversion of units in the middle of a test, but your textbook does do that sometimes. So, but when you're doing homework, you have time to look up things and find out what that is. Anyway, so the liters is volume. The 1,000 cubic centimeters is volume. And if you have a cylinder, you're taking the area of a circle and sliding it through the height. So the volume is the area of the circle multiplied by the height. And we found out that volume is 1,000 cubic centimeters to go with the other units. Actually, you know what? It didn't even say to use centimeters, which is, it should have said a little bit more in the problem. Now, I have a choice of either isolating H and plugging it into the 1H, or isolating R, which is meaning I'm going to have to get a square root involved and plugging it into 2 different R's. What a choice. So if we want to avoid extra work, we're going to isolate that H. And then substitute that into the H that is right there. And I'm going to shrink my screen so that I can write the formula over here. So I've got the 2 pi r squared from here, and then I'm writing plus 2 pi r, and then substituting an H. I now have a formula for surface area with respect to one variable. Now, we can take a look at the graph that this creates. And I have reminders of what to change my settings to be able to see this one. And X is 10, while Y is 1,000. There we go. So if you look over here, you can see that the X variable is right where that R is. And this is the simplified form. And then my function b of x, the y value is representing that surface area that we want to minimize. And we can see that there's a nice little minimum going on. Now, technically, we're supposed to think about the domain. Radius is the input variable. The radius needs to be a positive number. Would you agree? But how big can the radius get? That depends on how thick the material is, really. So we don't have a set endpoint for R for what it is largest as. And I'm going to talk to you about what the AP test would expect with justification. But first, just see that this is the graph of input horizontal representing radius of that cone, and that output is representing the surface area based on that radius number. And we should be able to use calculus to get this number right here. Desmos is really nice about showing special points. Don't you wish your calculator did that? Yeah. All right. So I'm going to go back over to the problem. And now we're going to start the calculus journey. First, I'm going to simplify so that my derivative isn't as extensive. The pi's cancel out, get a little bit of r cancellation, and I wind up with 2,000 divided by r. But I'm going to write it as 2,000 r to the negative 1 because that's going to be an easier derivative to take than quotient rule. Then I look at the rate of change of surface area with respect to the radius. So I'm taking the derivative with respect to r. Then my next step is that I need to find what makes the derivative equal to 0 or undefined. It's very important when you need to solve an equation. If you have a negative exponent, force it to change the side of the fraction it's on and become positive, or you have the likelihood of making a silly error. Because I've seen that silly error too many times on tests, and you don't want to accidentally see this as r squared. Now, if I'm going to solve for what makes this equal to 0, I've got to first get a common denominator. So if I multiply by r squared, I will end up with this by multiplying top and bottom by r squared. And now I can see that that fraction is 4 pi r cubed minus 2,000 over r squared. Now, this function is undefined when r is 0, but it doesn't make sense in the domain. If you don't have a radius, you don't have a can. So while 0 is a critical number of that equation, it's not in the domain of consideration. So now the only thing I need to do is solve for what makes the numerator equal to 0. If you don't have a calculator available, this is a hideous looking number. Just know that anytime you are testing and you are not allowed to use a calculator, you are allowed to leave your answer looking like a mess. So if I add 2,000 and then divide by 4, that's going to give me 500. Then I divide by pi, and then I cube root. You would leave your answer this way if you had no access to a calculator. And that's perfectly fine. If this was an AP exam, I would say just leave it there. Don't give yourself the opportunity to write an incorrect answer. Wait, I just noticed something in the chat. How long ago was that written? A minute ago. It would definitely minimize the cost for metal, though. Oh, for the radius to be 0. That was a joke. That was funny. Okay. Now, logically, are you with me? Logically, you can understand that this is the optimum radius. For a multiple choice problem, you're doing as little work as possible. For a test that I give you on this, I'm actually okay if this is all you show me. I need to see that you have an equation. Yes, this is in centimeters. I need to see that you have an equation with respect to one variable. I need to see that you take its derivative, and I need to see that you solve for its critical numbers. And then I need an answer. So know that I am okay with that little of work. But if this were on an AP exam, and it's free response, they expect full justification. However, this problem does not have a specific endpoint on the right end. So I'm going to tell you about another way that you're allowed to justify on the AP exam, and let me tell you, this is very important. Solving absolute maximum minimum, whether it's an optimization word problem or something that's just similar to an optimization word problem. It shows up in free response very often, and it shows up in multiple choice. It's a big deal, and you have to know what's expected for justification, because the justification, if you don't have it right, will lose you at least half the points if you do not have proper justification. So I showed you the proper justification a moment ago if you have specific endpoints and all your critical numbers between the endpoints. That is a justification acceptable in the AP exam. But if you don't have endpoints to compare, you are probably in a situation with one critical number only. If you have only one critical number, you can use this. And again, this is extremely important for those of you taking the AP exam. You may need to use this reasoning and have it be worth a few points that are very valuable. Understand this is not the first derivative test for relative maximum minimum, but it is similar to it. The key things that are different is that you have to explain the domain. When you're explaining a relative maximum, it's sufficient to say that f prime changes from positive to negative at C. But if you're in an absolute maximum justification, you have to express for all x less than the critical number within the domain, you have a positive first derivative. And for all x greater than that critical number in that particular function's domain, that your derivative is negative. And then vice versa for minimum. So make sure you're very, very clear on what is expected to justify absolute maximum minimum. These are the two ways that they're looking for. I'm going to keep going because you can write this down later. It's in your textbook, and it's also, you can look at the video later if you desire. And I'm going back to the problem. And so For this problem, you're dealing with a domain where R is only positive. So how do you need to specifically write this where it justifies that this is the location of minimal cost? And I'd love to give you time, but we don't have time. So you need to be looking at the derivative formula of surface area being positive versus negative. If R is between 0 and the critical number, and I need to present 0 because if I don't, then I'm going into imaginary territory because the radius can't be negative, and you want to acknowledge that. Wait, what am I doing? I just started writing the cube root, and then all of a sudden I realized I was copying the function, not the number. Okay, so you need to express that for this interval, the rate of change of surface area, and you need to decide if it's negative or positive. And let me tell you that when I look at this, what I'm seeing is if this R is super, super close to 0, 2000 is going to cause a negative to happen. You can find a small enough number for R to make that numerator negative. You don't need to plug in specific numbers and sit there and try to figure out if it's positive or negative. You can logic your way through by thinking on the extreme ends. So a very small positive number will definitely cause a negative numerator. And you can say that the derivative of surface area is less than 0. And then for all R greater than that critical number, the rate of change of surface area is positive, and you can double check because if R is just anything larger than that number, pick something, just imagine ridiculously large. Can I get this term to be larger than 2000 if I have no boundary to how big I make R? Yeah, so I'm good there. This is your justification to then say that the minimum happens at this R. So surface area and thus cost is minimized when the radius is equal to that number. And after that, you just make sure that you answer the question that they asked you. Have you ever done, well, I'm sure you've tested on something where you thought you were done, but there was more. It's always a horrible feeling. You can look at this video later, but I've got to get you started on the quiz. And I will try to make some more videos over the weekend with the rest of the examples. This asks for the dimensions, so just know that from there, you need to take that value of R and plug it in here to get a value for H, and then you've got your dimensions. All right, I'm stopping the recording, and I'm going